Hi class. Today we're going to be working on Chapter 15, Virtualization and Cloud Computing. Virtualization is kind of a more difficult concept to grasp at a sort of in-depth level. We're going to go through it in multiple layers throughout this chapter. So if it doesn't quite make sense right away, don't worry too much. We're going to, again, keep going over it and going over it. And I think all the pieces will start to come together at some point. So don't panic too much if it sounds sort of extremely complicated and abstract. I'm going to go ahead and start with a sort of Wikipedia introduction or explanation into virtualization. I just kind of like the way they describe it. So let me go ahead and start with that. Virtualization. In computing, virtualization is the act of creating a virtual rather than an actual version of something, including virtual computer hardware platforms, storage devices, and computer network resources. So again, the kind of idea there, virtualization, is we're creating a virtual version of something, or virtualizing it, rather than using the physical or actual version of something. Again, this can be creating a virtual version of an entire device, or sometimes virtualizing a specific process or aspect, abstracting some process or abstract away from or functionality away from a device and virtualizing that. Oftentimes when we talk about virtualization, most people think of something like a virtual machine, a VM, an environment that imitates a physical machine, installs and runs operating systems as if it was its own physical computer. Hardware underutilization is a common problem when we're talking about regular computer resources. So oftentimes when you're even on your personal laptop, if you're just browsing the web or watching a movie, you're not using the entire power that that device is capable of. You're not using the full computing power available. That may not be a big problem on a personal laptop, but when you have these massive data centers with a tremendous amount of storage capacity and computing power, it's a big waste and a big cost for them to do nothing sometimes and then use a tremendous amount of resources other times. So we need to find ways to use those resources efficiently. A little more on fixing underutilization. Essentially, the idea is we need servers to do more with the given hardware. So with the hardware and resources that they have available, we need them to accomplish more. Or the main idea there is that we want to use as much of the hardware resources that are available as we possibly can. So we want it to be efficient. We don't want it to go to waste. PC processors are capable of multitasking. They can handle multiple applications or tasks all at once. And that same functionality allows processors to handle a bunch of virtual machines. Hardware virtualization. Hosts run multiple operating systems simultaneously. A little bit more on virtual machines. Essentially, it is a special program that runs in a protected space, enables all server features to run as though they are each separate computers. So it's essentially treating these virtual systems as if they are a fully functional, independent, real computer. Hypervisor, a program that creates, runs, and maintains VMs. So the hypervisor is doing the job of creating, running, and maintaining the virtual machines. A guest virtual environment, this is where the operating system is installed. I think this is a pretty good graphic that's going to help us visualize what we're talking about here. So on the left, we have a kind of classic computing scenario. We have our different applications that a computer may be using. We have the operating system and then the hardware that we're using. So the hardware, that's your CPU, GPU, storage devices, memory, all that kind of stuff. The operating system could be something like Windows, Linux, Mac OS, any of that kind of thing. And then these applications, web browser, video games that you're playing, any of that kind of stuff that you're using, any of your kind of applications or programs on your computer. And how this normally will work is your applications will need a certain amount of resources, the computing power, resources from the GPU or memory or some kind of storage on your device. And the operating system will help manage all those resources. So they'll communicate directly with the different hardware and manage those resources for those applications. In a virtual computing environment, it's similar, but now we have a hypervisor in the mix that is creating virtual machines. So there's, again, different configurations for this type of thing. This is just one setup that I think kind of helps us to visualize what's going on. But here we have 3 different virtual machines. We could have many, we could have fewer. And the applications will communicate with the operating systems on the virtual machine. And again, these could be Mac, Windows, Linux. They could be all the same operating system. They could be separate operating systems operating in each of these virtual machines. and then they will communicate with the hypervisor, or the hypervisor is responsible for creating these virtual machines, managing the resources and all that, and it will communicate with the hardware directly. And again, same kind of hardware as we're using before. This will be your physical hardware, your CPU, GPU, storage, all that, and it will take that and it can create virtual storage and virtual memory, all of that kind of thing, all of the resources that these virtual machines will need. Here we have an image of Ubuntu Linux running in a virtual machine. The specific software used right here is called VirtualBox. And we see that this Ubuntu Linux virtual machine is running on a Mac computer. So this Mac computer is running a separate kind of isolated virtual machine on it. And again, the operating system that's using is Ubuntu. Just an FYI, VirtualBox is a free program. You can download, just get on Google and download VirtualBox, and you can download Ubuntu Linux for free as well. And you could set up a virtual machine for yourself if you wanted to. Just one FYI, you may want to make sure your computer has a little bit extra system resources. You need a kind of okay computer to do that. If it's already a little bit slow and clunky, you may have a hard time sort of running a second isolated machine on your computer. Let's talk a little bit about a type 1 and type 2 hypervisor. We discussed a type 1 setup a little bit ago, but I'm just going to kind of recap on what's going on there. A type 1 hypervisor is installed directly on the hardware resources. So it accesses things like the CPU, RAM, all that kind of the storage. It accesses all that stuff directly, and then it manages that and helps to allocate that to the different virtual machines. And that is how that setup works. A type 2 hypervisor, on the other hand, we have an operating system installed directly on the hardware, and then our type 2 hypervisor is installed on the operating system. So again, type 1, the hypervisor is accessing hardware resources directly, whereas a type 2 hypervisor is installed on top of an operating system before the hardware. And so the type 2 hypervisor will coordinate with the operating system to manage different system resources that are available. That VirtualBox program that we just talked about a little bit ago would be an example of a type 2 hypervisor. If you're running Windows, Mac, whatever it may be, you can install that VirtualBox program on top of that and create virtual machines from there. Abstraction. So this has a few different definitions, and it'll come up a lot in virtualization. So we're going to kind of talk about some of the different definitions that you need to know for abstraction. So in a general definition for abstraction, or to abstract, is to remove or separate. So when we're talking about relevant to virtualization, we're talking about taking one aspect of a device or process, and we're going to separate it from that device or process. So we're abstracting one aspect of a device or process. So here's an example, and we kind of talked about this before, but we're just going to kind of cover it again. An operating system that is separated from the hardware and being placed in a virtual machine. An OS is abstracted, again, removed a step from the bare metal in the computing hardware. So just the kind of example that we were just highlighting a little bit ago. That is an example of abstracting a device or process away. This one feels a little bit jargony, but I'm going to try to run through it anyway. Abstraction, the process of abstracting something complicated into layers that lets us focus on a few issues at a time. Abstraction is both a concept and a noun, defining the process of separating functions into discrete units. Those discrete units are called abstractions. When we're talking about abstraction, when it comes to computing, we're usually talking about a specific kind of abstraction. We're talking about a pattern that involves creating a virtual or a software version of something. So we're creating a software version of something, this virtual version rather than the physical real world existing version of something. Most kind of virtualizations will replace an existing component with a layer of software. Virtualized software is roughly indistinguishable to any programs, devices, or users that interact with it. So again, they're roughly identical to the real thing, or virtually identical to the real thing. Here's some examples. Virtual memory replaces direct access to physical RAM with a layer of software. Hardware virtualization replaces all of the physical devices an OS needs with software versions that the hypervisor controls. Storage virtualization replaces a system's hard drive with a software block storage device. Network virtualization creates software versions of networking functions. So this last one is definitely, all of this is relevant to what we do in this class, but this is probably one of the more relevant aspects that we need to consider. And again, this is another pretty big diagram that's going to help us kind of understand what's going on. So this is the classic networking model. We have this physical layer 2 switch. We have physical DNS server. We have physical intrusion detection device. We have a firewall or router. And again, these are all physical devices on our network. In a virtualized network, we can virtualize those things. So we have our system hardware or our devices hardware. So again, same thing as we've been talking about, CPU, GPU, all that kind of stuff. Then we have our hypervisor that is installed directly to the bare metal. And then we have we've virtualized these other devices. So virtual layer 2 switch, virtual DNS server, intrusion detection, firewall router. So these are just software versions of these hardware components. And I definitely think we can see how this is kind of a cool concept and definitely beneficial to what we're learning about in this class. Let's talk a little bit about flexibility. Generally, replacing hardware components with software components will add some flexibility, as you might expect. One other thing we need to talk about is inputs and outputs when it comes to that. So generally, if you have a switch or some kind of hardware device, normally you would interact with that by plugging in a cable, or if you want to install something, you use a USB drive, flash drive, or some kind of disk, some sort of way you're physically interacting with these things to install, update, or manipulate them or manage them. However, in these virtual devices, we don't have those physical ports. That doesn't mean you can't manage these devices. Most of these virtual systems will have some kind of equivalent to a physical port to route inputs. And again, for outputs, similar situation. We have all kinds of virtual options. In some cases, you have more. This is a screenshot of installing Windows 11 on a virtual machine, just to kind of highlight that point that we were just talking about before. This is definitely one of the aspects of the flexibility for virtualization that is extremely important and makes virtualization so popular and such a powerful resource for many different companies and organizations. And that is the ability to divide and combine resources. So we can pull resources up and kind of dynamically allocate them wherever we need them, whenever we need them. And so that makes virtualization extremely powerful. Oftentimes you have some kind of service or a situation where you need a tremendous amount of resources in one area, but only for certain periods of time or short periods of time, and then all the rest of the time those resources would be wasted. So if you were to dedicate real physical machines to that, again, they would only be used for a short period of time, and then the rest of that time it would be a waste. However, with virtualization, you can use that to allocate those resources to them when they need it, and then take them back when you don't. So again, just to kind of put that in a nutshell, one of the key aspects of virtualization that makes it very flexible and very powerful is that we can dynamically kind of allocate, divide, or combine our computing power. When it comes to scaling, virtualization can definitely be extremely beneficial as an organization grows. For smaller environments, or at least for the average home user, virtualization may not be a massive game changer, but when we're talking about massive data centers, virtualization can save organizations millions or billions of dollars. All right, let's talk a little bit about cloud computing. One way people like to describe what the cloud is essentially just someone else's computer, someone else's device, someone else's data center. And that is an okay kind of comparison to it. Your book explains why maybe it's not the most accurate description, but I definitely like to use it. So I might a couple more times throughout this chapter, because I think it's a good way to kind of easily visualize or kind of understand what's going on with cloud computing, or at least get a general understanding of the idea. A slightly more accurate description would be to compare it to something, or a more accurate analogy would be to compare it to something like a cafeteria or a restaurant of computing and networking resources. The idea would be you have a big cafeteria, and as different people need different resources, they come in, acquire the resources they need, and then leave. So, and again, the other people's computer kind of analogy comes in, because if you're storing something on something like Dropbox or Google Drive or Microsoft OneDrive, essentially what you're doing is you're just taking all of that information that you had stored on your computer, and you're just storing it on Microsoft's or Google's or whoever else's storage devices. So essentially you're just kind of storing it on their computer. And that is kind of where that analogy comes in. But again, it's a little more complicated, and that might not be, again, in all fairness, the perfect analogy for it. But it's an easy way for someone to kind of visualize the concept behind what cloud computing is. We generally break the cloud service model into three categories. Usually you'll see this depicted as a pyramid with software as a service at the top, platform as a service in the middle, and infrastructure service at the bottom. Again, the textbook we're using for this class likes to compare it to layers of a cake. That's fine too. We're going to go ahead and dive into what each of these layers are here in a second. Infrastructure as a service, IaaS, is usually the most complicated of the three, or generally requires the highest skill level. So this is usually going to be your system administrators that use this option. Let's go ahead and run down the kind of textbook description here. Software building blocks, service provided by large-scale global providers who use virtualization to minimize idle hardware, protect against data loss and downtime, and respond to spikes in demand. Some of the benefits: no longer need to purchase and administer expensive, heavy hardware. You pay to use the provider's powerful infrastructure as a service while you need it. And then when you no longer need those resources, you can just release them and you stop paying for that. So you only pay for the resources you use or need. This diagram here on the right is kind of a big picture of the hardware and resources kind of generally that an IT team would have to manage and be responsible for. In infrastructure as a service, the provider or vendor will manage these things: networking, storage, servers, and virtualization, while your IT team will have to manage the OS, middleware, runtime, data, and applications. Things you may do with this model is manage virtual machines, storage, firewalls, and networks. Platform as a service, this is something that you'll often see developers use. So platform as a service, PaaS, a complete deployment and management of systems that gives programmers all the tools they need to administer and maintain a web application. The goal is often, again, running a web application. So in this scenario, the vendor will manage networking, storage, servers, virtualization, the OS, the middleware, the runtime, and your team will only have to deal with data and applications. So again, this is why it's definitely used often and ideal for web development and web applications. These are some examples that you might encounter. Software as a service. This is the kind of web application that end users will usually interact with. It could be something like YouTube or Gmail, Dropbox, that type of thing. The application runs on a server, so it's not something that you necessarily have to install on your own PC or local device. You can just access it with a client. So again, like when you want to access YouTube or Gmail, you just go to that website, log in, or do what you want to interact with that application. And again, this is the kind of visualization of software as a service. The vendor will take care of all of this: networking, storage, servers, virtualization, OS, middleware, runtime, data, and the application itself. Okay, this is just the kind of big picture look at everything we just talked about. So in an on-premise setup, this is where we're basically responsible for managing everything in the stack. Infrastructure as a service, the vendor will manage some key things like networking, storage, servers, and virtualization, and will be responsible for managing the rest. Oftentimes, system administrators will make use of this option. Platform as a service, this is something that devs will like. So if you want to develop a web application, this is going to be an ideal service. And again, in this situation, vendors will manage networking, storage, servers, virtualization, OS, middleware, runtime, etc. And then whoever's using the platform as a service will be using data, or will be responsible for data and the applications. And then software as a service, again, this is something that's usually designed for an end user where they're just interacting with the web application. Cloud deployment models. There are a few types of cloud networks. We have a public, private, community, and hybrid. Let's go ahead and get into each of those. Let's start with public and private clouds. So a public cloud is software, platforms, and infrastructure that are generally or that the general public can sign up for and use. So there may be a fee or something like that associated with it. There almost certainly will be some sort of fee or cost associated with that. Typically, this is just referred to the cloud. So when we're talking about the cloud in general, usually it's going to be the public cloud that we're talking about. Private cloud, this becomes an internal cloud that the business owns. So this is not something that anyone can sign up for or have access to. It's something that is usually a private business will create, set up, and organize. It gives them some of the flexibility of cloud infrastructure and allows the business to have complete ownership of its data. So usually if security is extremely important, a private cloud is an ideal option. Community and hybrid clouds. A community cloud is very similar to a private cloud. The difference is multiple businesses, organizations, or users are collaborating to pay for or manage that cloud infrastructure. Usually it's good for when organizations have similar goals or needs. A hybrid cloud is just some combination of a public, private, or community cloud. Virtualization is obviously an extremely important part of cloud computing, or a very beneficial or important part of cloud computing. It helps many massive data centers that comprise the cloud scale up or down efficiently. Providers can set up everything a customer needs in real time. They can allocate those resources or release those resources just as quickly. So it allows us to very, very efficiently manage cloud computing. Let's talk about infrastructure as code. IAC. It helps network applications and services with scaling, abstracts the infrastructure of an application or service into a set of configuration files or scripts. 3 parts of the concept. We're going to talk about hurdles faced by organizations, automation as options, and orchestration. Scaling problems. These can occur as networked applications and services grow and mature. We can have problems coordinating programmers, or programmers coordinating with each other. As applications grow, they can become increasingly difficult to test and set up or evaluate how the different components are working together. As databases grow, sometimes they can be too big to fit on a single physical server. Automation. As applications scale up, they can sometimes create huge maintenance issues where it takes a lot of hours for people to maintain or service these applications and systems. So with automation, we're using some kind of code to replace the tasks that people would manually do. So these things will be carried out automatically, hence the name automation. So good candidates for automation would be multi-step tasks performed frequently, infrequent tasks that you might forget the steps for. Orchestration. I like to think of this as just a kind of bigger version of automation. It's not a perfect description, but it kind of helps me remember what we're talking about. So orchestration combines automated processes, creates bigger, multifaceted processes called pipelines and workflows. Streamlines development, testing, deploying, and maintaining workflow. A special kind of orchestration to remember would be CI/CD, which is continuous integration, continuous deployment. It triggers an automatic multi-step pipeline and verifies validity of a change. Again, as we mentioned before, virtualization and networking is definitely one of the critical concepts we want to kind of think about and understand in this class, because virtualization is definitely transforming networking. Software can perform many of the classic network functions that we need very expensive hardware devices to do. Some of the key topics that we're going to cover here shortly would be virtual networks within VM hosts, virtualization of switching and routing. We're not going to cover this, but the textbook talks about breakout of the VM host and network function virtualization. This last bit is kind of repetitive, just kind of reemphasizes a lot of the concepts we've already talked about. Virtual networking inside the VM host. Just because you're using a virtual host or virtual devices, it doesn't mean that you're going to get away from or escape a lot of the complex networking requirements that we've been learning about. So you're going to have to deal with a lot of the same complex networking requirements and some of the some additional ones as well. You may need, for example, you may need to share a private network to collaborate. You may need to serve requests from the open internet. You may need to be isolated from the network. You may need to rapidly reconfigure the network as VMs come and go. Hypervisors may have their own basic networking capabilities, like a built-in switch, that will help you deal with some of these complexities. You can also run other network functions as VMs. One challenge with virtualization, as you guys might expect, is if we have one physical server running a number of virtual machines. Could be dozens, could be hundreds. How do we deal with that when we only have the one network interface card on our single physical server and we have hundreds of virtual machines that are acting as their own independent machines? Essentially, the idea is we use virtual switches and virtual network interface cards. Ideally, that virtual network interface card or that virtual switch will function indistinguishably from its real-world counterpart, or almost indistinguishably from its real-world counterpart in a practical sense. So one of the oldest and simplest ways to go about this is we bridge the NIC, or sometimes it's just referred to as bridged mode. Each bridge is a software connection that passes traffic from the real NIC to a virtual one. So in our diagram here, we see that we have several virtual machines, and each of these machines has a virtual NIC. Now it's important to note, again, as we already emphasized, that these virtual NICs should behave essentially identical to a real network interface card. They should have a MAC address that is a legitimate, unique MAC address, just like our real physical network interface card has a real MAC address that is unique. These will operate at the layer 2 of the OSI model, same as the real network interface card. Distributed switches. So virtual switches also need to be configured and managed because, again, remember, they're essentially identical or at least very, very similar to a real-world physical switch. So we still need to manage and configure these virtual switches. Virtual switches will normally use some kind of web interface for configuration. Again, quick growth requires careful configuration for every new virtual switch added to an existing virtual switch, or added to existing virtual switches in a large, complex, single virtual network. Distributed switches. This is kind of a textbook definition for this. The centralized installation, configuration, and handling of every switch in a network. Every hypervisor has some form of central configuration of critical issues for switches. So this covers things like VLAN assignment and trunking. Virtual routers and firewalls. We're going to keep this one kind of basic. Virtual routers allow dynamic network reconfiguration. Virtual routers are just VMs like any other VM. We can allocate more resources to them as traffic grows. Virtual firewalls can protect servers, again, just like real firewalls. Useful for cases where installing a physical one would be hard, costly, or almost impossible. Network function virtualization, NFV. I apologize, this next section is going to be a little bit jargony, or at least these next few slides that we're going to cover. Even for a networking class, it definitely gets a little bit rough. A networking architecture. So NFV is a networking architecture. It's not an actual feature that you can implement, it's an architecture. Applies an infrastructure as a code style automation and orchestration to a network management. So again, applies infrastructure as a code style automation and orchestration to network management. Network function virtualization infrastructure, NFVI. So we're tacking the I on the end for infrastructure. This, when we're talking about this, we're talking about the hardware and software that form the foundation of a virtual network: servers, storage arrays, switches, etc. NFVI, network function virtualization infrastructure. So virtualized network functions run on NFVIs. They run on the network function virtualization or virtualized infrastructure: firewalls, load balancers, routers, etc. Traditional networking devices have a control plane and a data plane. They have a control plane and a data plane. The control plane decides how to move traffic, and the data plane will execute those decisions. In an SDN, a software-defined network, we outsource the control plane. So we'll have some kind of centralized controller here that helps to decide how to manage traffic. The SDN controller is programmable. It runs software applications for jobs like load balancing, optimizing traffic flows, threat protection, and more. SDN uses new planes to manage the complexity caused by separating infrastructure and control planes. So the fact that we separated the infrastructure and the control planes in an SDN creates a little bit more complexity, and we introduce two new planes to help manage that: a management plane and an application plane. So SDNs and NFVs are not necessarily mutually exclusive. They are separate, complementary ways to manage networks. SDNs virtualize the control plane and outsource its work. NFVs virtualize the entire network function. NFVs often can take advantage of SDNs. One important note is that the textbook that we're using in CompTIA may use different language for these things at different times. The N10008 objectives list 4 terms under software-defined networking: application layer, control layer, infrastructure layer, and management plane. Those are the same things that we just talked about. The only thing here is it's just a different word or different term for the same thing. For example, the control plane is just the control layer. The infrastructure layer is the data plane. So that's the one that's a little bit trickier. The infrastructure layer becomes the data plane. The control layer just becomes the control plane. Okay, that's all I have for you guys this week. I hope you enjoyed the video and the information that we covered in here. There are two more important sections that this textbook covers that I think are worth looking at, and that is desktop as a service and interconnecting local and cloud resources. I hope you have a wonderful week. Bye.